B hadn't yet disappeared, and I got some charge. That's not the conservation of charge against the laws. So the other fellow says, yeah, but you're moving. He says, how do you know? And so on. I think you're moving. So if we are unable by any experiment to see a difference in the physical laws whether we're moving or not, if the conservation of charge were not local, we could tell when we were, you see, if it were not local, only a certain kind of man would see it work right, namely the guy who's standing still in an absolute sense. But such a thing shall be impossible according to Einstein, and therefore it's impossible, according to the relativity principle, to have non-local conservation of charge. This conservation, the locality of the conservation of charge is consonant with the theory of relativity, and it turns out that locally, that this is true of all the conservation laws, not just the charge. As you can appreciate, if anything is conserved, it's the same principle. Now, another interesting thing about charge, which has nothing to do with the conservation law and is independent of that, is a very strange one for which we have no real explanation today. And that is that the charge always comes in units. When we have a particle that's charged, it's got one charge or two charge or -1 or -2. It's a nice little lumpy unit and has nothing to do with the conservation of charge, but I can't help writing down that to find out it comes in units, the thing that's conserved. And that's very nice that it comes in units, because that makes the theory of conservation of charge very easy to understand. It's just a thing which we count, which goes from place to place. Finally, it turns out technically that the total charge of a thing is very easy to determine electrically, because the charge has a very important characteristic. It's the source of the electric and magnetic field. Charge is a measure of the interaction of an object with electricity, with electric field. And so the other item that we should put here on the list is that this is the source of a field. In other words, the electricity is related to the charge. So the particular quantity which is conserved here has two other aspects which are not connected with the conservation directly, but are interesting in either way. One is that it comes in units, and the other that it's the source of a field. Are there other examples? There are many conservation laws. I give some more examples of conservation laws of the same type as the charge, in the sense that it's merely a matter of counting. There is a conservation law called the conservation of baryons. A neutron can go into a proton. If we count each of those as one tien, then we don't lose the number of tiens. The word tien is actually substituted by baryon, which is equally mysterious and meaningless. The neutron carries one baryonic charge unit, or represents one baryon. Then a proton represents one baryon. All we're doing is counting and making big words. And so the total number, if this reaction occurs, the total number of baryons doesn't change. It does turn out, however, that there are other reactions in nature. For example, a proton plus a proton can produce rather great variety of strange objects. A lambda, a proton, and a K plus, for instance, which are, these lambda and K plus are names for peculiar particles. Now, from this one, you know you put two baryons in, you see one come out, so possibly one or the other is one. But if you'll study the lambda later, you'll discover that it very slowly, this is easy for it, and this is hard for it to do, it disintegrates into a proton and a pi, and ultimately the pi disintegrates into electrons and whatnot. But what you've got here is the baryon coming out again. So we think that the lambda has a baryon number, but the K does not, has 0. And so in counting these other numbers, we have a similar situation with baryons. So we have charge, and then we have baryon number, with a special rule that the baryon number is the number of protons, plus the number of neutrons, plus the number of lambdas, minus the number of antiprotons, minus the number of antineutrons, and so on. It's just a counting proposition. It's conserved. It comes in units. And nobody knows, but everybody wants to think, by analogy, that it's the source of a field. We are trying to guess at the laws of nuclear interaction. And the reason we make these kind of tables is this is one of the trick ways of guessing at nature. If this is the source of a field and this does the same thing, it ought to be the source of a field too. Too bad so far it doesn't seem to be, or for sure isn't anyway. We don't know. Sometimes people think it is, sometimes not. We don't know enough to be sure about that question. Now it turns out that there is a very peculiar thing. I would like to mention, there are one or two more of these counting propositions called lepton numbers and so on, but you learn nothing new, the same idea, just counting. There is one, however, which is slightly different, is that there are, in nature, characteristic rates, apparently, with these strange particles. There are rates of reactions which are very fast and very easy reactions to do, and others that are very slow. I don't mean easy and hard in a technical sense. It's a little, actually doing the experiment. It's got to do with the rates at which these reactions occur when the particles are present. Anyway, there's a clear distinction between this kind of a reaction and this. And it turns out that if you take only the faster, easy reaction, that there's one more counting law in which the lambda gets a -1 and the K plus gets a +1, and it's called the strangeness number, or hyperon charge, rather. And the proton gets 0. And in that particular rule is right for every easy reaction, but it's wrong for the slow reaction. And then we have a conservation law called the conservation of strangeness, or the conservation of hyperon number, which is nearly right, which is very peculiar. So that's why the stuff has been called strangeness, the number. It's nearly true, and nearly true. But in trying to understand the strong interactions which are involved in nuclear forces, since as far as the strong interactions are involved, the thing is conserved, that has made people propose that for the strong interactions, that's again a source of a field, but we don't know. But it's this, I bring these matters up to show you how the conservation laws are used to guess new laws. Now there are other conservation laws that have been proposed from time to time of the same nature as counting. For example, chemists once thought that no matter what happened, the number of sodium atoms stayed the same. But sodium atoms are not permanent. It's possible to transmute atoms from one to another, so that one is just true. Another law, which was for a while believed to be true, was that the total mass of an object stays the same. It depends on how you define mass and whether you get mixed up with the energy nowadays, and I will disregard this mass law until we come to the conservation of energy. But the mass conservation law has been contained in the next one, which I'm going to discuss now, which is the law of conservation of energy. The law of conservation of energy is the most difficult, abstract one, and the most useful, as a matter of fact, of all the conservation laws. It's more difficult to understand than the charge and these other ones, because in the charge and these other ones, it's obviously merely, the mechanism is perfectly clear. It's a conservation of the object, sort of. I mean, not quite, because of this problem that we get some new things from old things, but it's really a matter of counting. But the conservation of energy is a little more difficult. Here we have a number which is not changed in time, but the number doesn't represent the number of any particular thing. I would like to make a kind of silly analogy to explain a little bit about it. And I want you to imagine that a mother has a very difficult child. Well, not necessarily difficult, but she has a child who she leaves alone in a room with 28 blocks. The indestructible, absolutely indestructible blocks, like the charge. And the child plays with the blocks all during the day, and when the mother comes back, she discovers, indeed, there are 28 blocks. She checks all the time the conservation of blocks. Well, this goes on for a few days until one day when she comes in, there are only 27 blocks. One block she finds later outside the window. He threw one out the window. So first we must appreciate that conservation laws involve that you watch out that the stuff that you're trying to check doesn't go out through some wall. And the same thing could happen the other way if a boy came to play with him and brought in some blocks. Of course, those are obvious technical matters that you have to be careful of when you talk about a conservation law. But now suppose, however, that when the mother comes to count the blocks, she finds there are only 25 blocks, but suspects that in a little toy box, in a box that the boy has, he has hidden the blocks. So she says, I'm going to open the box. He says, no, you cannot open the box. How can she tell? She's a very clever mother, unlike most. She would say, the box weighs, I know when it's empty, 16 ounces, and each block weighs 3 ounces, so what I'm going to do is I'm going to weigh the box. So she would have another thing, number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces. And that adds always the same to 28. Goes on for a while until it doesn't check. What you notice is that the dirty water in the sink is changing its level. So we have the water level. Height of water in sink, minus 6 inches, which it is when there's no block in it, divided by 1/4 of an inch, which is the height that the water rises when a block is in the dirty water. Now, as the boy becomes more ingenious and the mother continues to be ingenious, more and more terms must be added on here, which all really represent blocks, but from a mathematical standpoint are abstract calculations, because the blocks are not seen. Now I would like to draw my analogy and tell you what is common to this and the conservation of energy and what is different. Suppose that you never saw the blocks at all, that in any one of the situations there were never any blocks. Then the mother would be always calculating a whole lot of terms, which is called blocks in the box, blocks in the water, blocks and so on. But there are other differences, that there aren't any blocks as far as we can tell. And that the numbers that come out here are not integers, unlike the case of the blocks with the child. Suppose, it could happen to the poor lady that when she calculates this number, it comes out 6 1/8 blocks. And when she calculates this number, it comes out 7/8 of a block, and the rest of them give 21, still 28. That's the way it looks. So what we discover is that we have a scheme in which we can find a sequence of rules, and from the rules, each one of the different kinds of calculations we call calculating the same thing, number of blocks, or energy, by different rules. And then we add all the numbers together from all the different forms of energy. It always adds up to the same total. But as far as we know, there are no real units. It's not made out of little ball bearings. So it's abstract. It's purely mathematical. There exists a number such that you can calculate and it doesn't change. I cannot interpret any better than that. And this energy has all kinds of forms, analogous to the blocks in the box and blocks in the sink water and so on. There is energy due to motion. It's called kinetic energy. There's energy due to gravitational interaction, the gravitational potential energy it's called. There's a thing called thermal energy, electrical energy, light energy, elastic energy in springs and so on, chemical energy, nuclear energy, and there is also an energy that a particle has from its mere existence, an energy that depends on its mass directly. That's a contribution of Einstein, as you undoubtedly know. E equals mc squared is what I was talking about, which is a famous equation, mystic law. Now, actually, although I mentioned a large number of energies, I would like to explain that we're not completely ignorant about the thing and that we understand the relationship of some of them. For example, what we call thermal energy is to a large extent merely the energy, the kinetic energy of motion of the particles inside an object. What we call elastic energy and chemical energy both have about the same origin, namely the forces between the atoms. When the atoms rearrange in a new pattern, some energy is changed. That quantity changes. That means that some other quantity has to change. So, for instance, if the chemical energy changes, then heat energy is changed. So that in a burning something, the chemical energy changes, and you find heat where you didn't have the heat before, because it all has to add up to it. But elastic energy and chemical energy are both interactions of atoms, and we now understand the interactions of the energies of the atoms, or those chemical interactions, or those interactions of the atoms, to be a combination of two things. One is electrical energy, and the other is kinetic energy. Again, only the formula for it is quantum mechanical instead of the usual. It's a little different one. Light energy is nothing but electrical energy, because light has now been interpreted as an electric and magnetic wave. The nuclear energy has is not represented in the terms of the others, but as a result of what we say, due to nuclear forces. Well, we didn't say anything. But nuclear energy is not connected yet to the others. I'm not just talking about the energy released. In the uranium nucleus, there's a certain amount of energy, and then when the thing disintegrates, it changes the amount of energy in the nucleus, but the total amount of energy in the world doesn't change, so a lot of heat and stuff is generated in the process in order to balance that thing out. Now, this conservation law is very useful. In many technical ways, And I wish I could give you a number of them.